Hi, we are MediMec and this is our second sprint presentation.
As the target audience, we selected Puerto Nariño and Leticia in the Amazonas department. Both of them undergo harsh conditions, which is why the development of a device for the COVID-19 vaccines is necessary. The requirements of this device are divided into two. First, the technical requirements, which are related to the engineering part of the project, and second, the requirements of the client. We also designed 5 indicators that collect the most important aspects of the device and with their respective reference values in order to evaluate the models we made. For the concept description and development, we also divided the system into two, heat transfer and vibrations.
Before we get into the development of the concept, we're going to talk about its description. So the specifications are: the heat transfer rate has an autonomy of 72 hours, the refrigerant mass is around 3 kilograms, it will have a volume of around 4,000 cubic centimeters. We haven't determined the assembly pieces yet because this depends on the amount of refrigerant and the way it's packed. The surface area is of around 1,400 square centimeters, and we haven't determined the vibration isolation, which we will talk about in further slides, but it will be measured in gravity. This is the geometric design that our system will have. As you can see, it's basically a cylinder with handles. We have two alternatives right now, and they vary in diameter and height, but they're basically the same concept. They have three pieces. The first one is the shell, in which the insulation material and the refrigeration material will be. Inside the shell are the molds. Each mold will be piled on top of another one, and each mold fits around 61 vials of the vaccine. And finally, the lid, which encloses the system to have it perfectly isolated. For the development of the concept, we had two types of prototypes. The first ones were virtual, and they focused on geometry, heat transfer, and vibrations, and physical prototypes, which we haven't done yet, which will focus on vibrations and calorimetry. The first prototype we made was a geometric one, and the objective was to generate a physical representation of the system, not only to see what it would look like and function, but also to have accurate measurements of volume and surface area that would be useful in future prototypes. With this information, we made the heat transfer analysis, and the objective was to determine the insulation wall thickness needed, as well as the refrigerant mass required so that the system would function in an established amount of time. The summary is here in the graph, where you can see total thermal resistance versus isolating material thickness for around 120 vials, and the prototype that won was prototype 11, which is the blue line that's highlighted right here, and it gave us a total of 5 centimeters of wall thickness, 3 kilograms of refrigerant, and that would give autonomy for 72 hours, which is what we had in the specifications.
For the vibration analysis, our objective is to determine a damping system that maintains the structural integrity of the vaccines. To achieve this, we use the data collected from a military motorboat, which shows that most of the vibrations occur in the vertical direction, have magnitudes between 0.6 to 0.8 gravities, and a frequency of 0.5 Hz. We also made a model which led us to conclude that the best material for this application should have a high value for the damping and stiffness coefficients.
Now we're going to talk a little bit about the physical prototypes. We haven't done them yet, but this is our plan. So the first one is the vibration tests. We're going to do this with the norm ASTM D99908 at the university with the vibration testing tables. We haven't chosen which one though, and we're going to use polyurethane foam because it's the best alternative we found with the investigations that we made based on our criteria and our ranges. We're also going to do calorimetry. We're going to do this on the polyurethane foam, but we're also going to do it on the refrigerant options like the gel, the PCM, and water. Theoretically, we've chosen PCM as our best alternative, but we don't know what's best practically, so we need to test that, and we're going to look for latent heat and thermal conductivity.
In this sprint, we found the quantity of PCM, the storage volume, the heat transfer rate, the surface area, a geometry with two possible arrangements, the components materials that are listed below, and we began requesting the materials needed.
For our future work, we will be doing physical models that include tests in a vibration table, calorimetry tests, and the manufacturing of the first prototype. For the analytical models, we will be follow-ups with the professors of the department and validating the results with the physical models. As for challenges, we have two issues to be discussed. First one is how to minimize mass flow when taking doses out of the device, and an integrated device for measuring temperature. Finally, we will be moving forward with the materials purchases.